that
This meeting is being recorded.
recording. Got it. Right. So let's start with some simple things because you don't have any background in differential geometry. So it'd be a good idea to start with the definition. So let's ask what is a manifold. So to answer this question, let me give you some motivations before I write the definition. So suppose, let's say if it's a function from R3 to R represents the temperature of the space, I mean our space now. At this moment, let's say, there's the function. So at each point in the space, it assigns a value, a real value, and that is basically the temperature at that point. Now you can ask interesting questions. Let's say, for example, which locations in the space R3 are the hottest? So there could be more than one location in the space out there, which is, just maximum temperature. Another way to say is at which points points, say P, the function attain its maximum. So, well, that's a question. And there are many ways to solve it. And one of the easiest way is we have nice calculus on R3. On R3, right? By calculus, I mean that the way of differentiating and integrating things, in roughly speaking. So you can, we can apply first and second derivative test. If you have any question, you can stop me and ask me. Tests. And I mean, you can compute the critical point, assume the function is smooth enough. You compute the critical points and then you see which critical points are local maximum or global maximum and so on. You can restrict this problem, this question, to a bit harder question. Let's say you restrict this function to the surface of the Earth. That would be a sphere. And then you get a function from the sphere. Let's say draw the sphere. Something like this. And now you want to know where, the function has maximum. So where the temperature is, higher than the other locations. And well, here, if you want to, let's say, use derivative tests, let's say you want to even define derivative of point P. The usual way is basically to take the small perturbation of F. So this should be pH minus F divided by value of H, and then it goes to 0. But in this definition, if you look, this P plus H go out of the sphere. So if you take P plus H, it will be something here. And therefore, this shouldn't work. So you want to differentiate along the surface of the Earth or the surface of the sphere. I mean, along the sphere. And you run into this definition with this problem of the definition. So if you are smart enough, you can still do this without doing some technical steps, because the sphere is sitting in R3 and you can still define somehow the derivative of such functions. But let's look into some more examples. In general, you can ask the following. So let M be any set. I mean, it's just a setup, some observations or something you got up during your experiment or something. And you have a function. And you can ask the same question. So question is, at which P, if any, in M, F attains its maximum. In this case, the function has no structure, no regularity. I mean, it's just a set and it's a function going from that set to R. So, I mean, this set, let's say it's some kind of, set up some observation you made during your experiment and you got some function, and this set, you don't know, any smoothness of it and so on. So you can ask, of course, this difficult question about it. So to answer this, one naturally think of the following. That is, maybe we should define calculus on M. It's on M first. So in order to answer that question, maybe you do define like the notion of derivatives and then all these stuffs, and then you handle this issue. So let's look into another example. Let's say you are in R3. And there is some object on the ground or whatever. You lift it to some other point along a path, this one. And you apply a force F. Now, how much work you did? Well, calculus would tell you the following, that if the path along which you took the object is described by this function R, that's the path it follows, and you apply the force, if from R3 to R3, that's the vector field, then what do you get is the work done is basically the integral along C of this F dr. That's how you do it. But now if you lift this object on a curved space, let's say, let me draw something curved. Like maybe the surface of donut. And you take an object and take it from one place to another one, like this. red is the path. Now the question is, let's say the path is again from this interval to this space, let's say M. Now, how much work did you do? Well, I mean, if you have nice calculus on this surface of donut, you can define it this way, this integral. So you need to be able to do some kind of integration over the surface of that donut before you define such thing. Well, so this motivates the following thing. So to do physics on, let's say, a set M, so this is any set, we need calculus. Right? Let's write down another example. It would be third, right? So let's invent an example. So take a rectangle in R2. This is sitting in R2, right? And let's say an object is moving in this inside this rectangle. But the rule is if the particle touches this, let's say this horizontal line, horizontal side, then it starts from, this way. So if it touches here, it starts from here, like this. And if it touches the horizontal sides, let's say here, then it starts from here. So the moment it goes here, it suddenly starts again here. That's the rule. So the object is moving like this with this rule. Now, with respect to the dynamics of this object, you don't differentiate between the horizontal side and vertical side. The motion see it equal, because if it touches one side, then it starts from the opposite side exactly parallel to that. So the motion is basically, if you glue this with this, so you identify these two sides, and then you identify these two sides, what you get is something like this, surface of donut. And now the object is moving, along on the surface of the donut. Now you want to describe the dynamics of this object. So more importantly, the trajectory. So the trajectory would be a gamma, would be a function from R to the surface of the donut. Let's call it T2. And if you want to find it out, you need to solve some differential equations. So let's say the derivative of this gamma would be some vector field. So that would be a equation for the motion of this particle. But the question is, how do you define this derivative again? Because the surface of donut is curved in this case. And I mean, if you are smart enough, you can still figure it out without doing much technical things, because this surface donut is sitting in R3. But if you take more complicated objects that don't sit in the Euclidean space, and you want to do dynamics for it, then and you want to write differential equations for it, you need to do calculus for that object. So this again say, we need to develop or to do calculus on the surface of the donut. So this moral of the story is the calculus you have in the Euclidean space is not everything. There are problems where you need to do this calculus on more curved objects like surface of donut, the surface sphere, and probably more complicated objects. So it motivates to generalize this analysis from the Euclidean space to objects that are not straight. It could be some curved type objects. Okay, so how to do calculus on general sets? So let's think of the following. The question is given a set, and you have a function from M to R. How would you define its differentiability? So take a point P, and let's suppose we have another function U from Rn to this set M such that it maps the zero vector to that point M. Suppose such a function exists. Now, if you compose these two functions, so you get f composed with U, you get a function from R into R, and now you know how to define differentiability. So let's say f is differentiable at P, I'm sorry, is differentiable at P if there exists another function from Rn to this set M with P such that the function this is differentiable at 0, right? That would be a sensible definition. And in this way, what you do is you upload, somehow upload the definition of differentiability from the Euclidean space to that set through a function. So, well, there would be a way of doing calculus on M by uploading the calculus from the Euclidean space to the general set M. But here you want to do something. What do you want in this case? So the differentiability I define, first of all, should not depend upon the choice I made. I mean, if I choose one function and you choose another function, then if the function is differentiable with respect to my function u, then it should be differentiable with respect to your function, which would be, let's say, w. So we want the following. The above definition should not depend on the choice u. Okay, that's one we want. Second thing is we want to define the calculus around every point of view. So for each point in M, we should have at least one function from Rn to this set M with the property of mapping to P. But if you can do that, then we can upload the calculus from Rn to the set. So the conclusion would be if M has the above properties, then we can upload. I mean, upload is not the right word, but for your, you don't have background, so that's the best term I can find for you. The calculus from Rn to M. Okay, that's the conclusion. And roughly speaking, going back to the question, what is a manifold? So manifolds, roughly speaking, are sets with the above properties, right? So manifolds are objects which could be curved, but they have this property that locally around every point you can find some function, and with this second condition, that this notion doesn't depend upon choice. So let's go to the precise definition of a manifold now. A smooth manifold of dimension n is a set. N is an integer, by the way. Is a set M together with a family up, ui's, and let's say u alpha and alpha belongs to some index set I, such that the following property holds. First one, so these u alphas are open sets in Rn, open sets for all alpha. Second thing is these xi's, these are basically maps from these open sets to M injective. They are injective maps. And the third condition is you want to do calculus around each point. So the images of these maps, so the union of the images should cover the whole set M. And you want the calculus to not depend on the choice of these maps. So let's say you impose the following condition. So if you have two indices for beta such that, the corresponding images of these maps intersect. Let's say it has a W which is not empty, right? Then the inverse images of these guys are open in Rn. And beta inverse composed with alpha, it would be a function from alpha inverse to beta. So this is a function. So this is a set in Rn. This is an open set in Rn. And this function has to be smooth. That's the definition, that these notions of differentiability I have defined above does not depend upon the choice of these functions. So there's a PEP condition, which is technical, which is there for technical reasons. So you just ignore it, but that is this family is maximal with respect to these conditions above. So this condition is just to make the classification problems of manifold well defined. So I mean, you can ignore it the moment. Let me draw a diagram for this condition to help you visualize what is happening. So let's say my manifold is this M. This is basically the image of U alpha, and then you have this image of U beta, and this is the intersection W that happens in E. Downstairs you have U alpha in Rn, so open set, and X is going from X alpha is going from this. Similarly, you have Rn and open set U beta, X beta is going from there. And now the inverse image, let's say it's here, that's basically X alpha minus this W, this portion. And you can somehow here do it here. Let's say this portion is X beta inverse. And now you have a function which is X beta inverse. This function is smooth. These are called transition maps. So this goes here and then come here. And you require these functions to be smooth. So M is any set. It could be very abstract set. It could be a group. I mean, anything. It's just a set. So question, right? So let me give you some examples. So maybe before I go to examples, I tell you that the definition of differentiability I gave you above is well defined, so it doesn't depend upon the choice of your function. So let's say you have a function from a manifold, and you choose X alpha going from to M such that the composition is smooth. Now, let's say I choose X alpha and I found that this composition is smooth because it's a function from Rn to R. Now, you found something else. Let's say you choose another one. Let's say X beta. Right? Now, the composition you would get is this one. And you can write it down like X alpha and then X alpha inverse X beta. Now, by my definition, this guy was smooth. So it's differentiable. And by definition of manifold, these transition maps are smooth. So the composition of two maps is smooth, so this one is also smooth. And therefore, if the function is smooth with respect to my choice of this local coordinates or local functions or local charts, you can say, then it's smooth automatically with respect to your choice. So the notion of differentiability I gave you about doesn't depend upon these choices. And that's because you have this extra interesting things. And it's not just the differentiability. If you later define integrals of differential forms, this condition would tell you that these integrals doesn't depend upon the choice of these local coordinates and so on. But for the moment, I think that's enough. Let me give you examples. So you take the sphere again. So these are basically points in R3 which satisfy this equation. It's the unit sphere. Let me draw it. So let's say this is y, x, and z. This is a manifold. So what are the local charts? Or what is the family of maps? I define definition. So let's say my one, you group from R2 to this sphere, and it's defined by x, y, two coordinates, 2x, 1 plus x square plus y square, 2y square minus, there's a third coordinate which is x square y square minus yeah, so one need to show that this point lies on the sphere. That's one thing. And the image of this map is basically the whole sphere, but only this point removed. So it miss the 0, 0, 1 point. So it covers the whole sphere, but just that one point. And can you tell me if I can find a map which covers the whole sphere? I mean, such a map which goes from R2 and but cover the whole sphere and is continuous. Yeah. So question again, can you cover the whole sphere with a map from R2, which is continuous and surjective? So it should cover the whole sphere. The image should cover the whole sphere, and the function has to be continuous from R2. Okay. I mean, for topological reasons, no, because sphere is compact and R2 is.
Sir, we know one type of mapping called stereographic projection from complex analysis, that if there is a plane and we define a mapping which touch each, which makes a line from every point of a sphere to a plane, and this is
right. This is what I define. So this pi 1 is the stereographic projection from the plane to the sphere. But it doesn't cover the sphere. It is an injective map for sure. It's continuous. I mean, you have to check if it's continuous. But it covers the whole sphere, but just the 0, 0, 1 point is missing. So my question was, can you find a continuous injective map from R2 to the sphere which covers the whole sphere? Well, that map would be homeomorphism, right? And for compactness reason, I told you you cannot do it because sphere is compact and R2 is not. So there doesn't exist such a map. So you need another map to cover that point. So what I do is I choose a function from S2 to S2 that rotates the sphere anyway, and that maps this missing point to the other point, 0, 0, -1. And I take the above, so I take another chart or another function, which is basically the above function, and then you rotate it with F. So now the image up pi 2 would be the whole sphere, but just this point missing. But anyway, the union of those two covers the sphere. And these are injective maps. It's basically the whole S2. You need to verify that it satisfies the conditions above. So it's a homework by you. You need to show that these maps are injective, and it covers the sphere, and the transition maps in this condition, this fourth condition. These maps are smooth. For this example. Anyway, so there are more examples. For example, the surface of this donut is a manifold of dimension 2. So because in the sphere case, these maps are going from R2, so that's basically dimension 2. You can draw more complicated figures. Let's say the surface with 2 holes, that's genus 2, and so you can go further. It's called genus 2 surface. Okay. So tangent spaces. So what is tangent space? Tangent line to a curve. This is similar to that. Let's say I have this sphere. I have a point here, P. Then you can look to the plane which is tangent to the sphere at point P. So it would be something like this. And let's note it by tangent at P to the sphere. This is basically vectors in R3, which is basically orthogonal to this point, this vector. So vectors such that V and P dot product vanishes. This is a 2-dimensional vector space. Vector space. Okay. For general manifold, you can do the same. So in general, so if you have manifold and you have a point P, then the tangent space of M at the point P is basically the setup. It's all tangent vectors. Tangent vectors. So for general manifold, it's very hard to draw it because this manifold is very weird. It could be in higher dimensions and you might not be able to visualize it. But what can we see is the observation. If I have R, let's say Rn as a manifold, my M is Rn, then I know that these vectors, let's say the ith component is 1. This form basis for Rn, right? So if I take a general manifold and I take a point P, then I know that there is a neighborhood of this point, and you can find a map from Rn, let's say alpha x, whose image would be this, because they exist by definition of manifold. So locally, you can identify this neighborhood of the point P with Rn. So the tangent space of M at the point P is basically would be spanned by these standard vectors, right? So you have this n-dimensional vector space. Here I'm cheating. These are not the precise way of defining these vector tangent spaces and so on. Even the definition of a tangent vector is basically you need to adapt it to the new setting and so on. But it's just one lecture and you don't have already much background in these things. So I would just skip the hard mathematics and focus on ideas. So now you have a tangent space to a manifold. You can define a better object. It's called tangent bundle. So if you have manifold M of dimension n, the tangent bundle is basically denoted by Tm, and it's basically the union of all tangent spaces. I mean, it's called tangent bundle because it's a bundle of tangent spaces. You can somehow draw this space. So let's say if this is your manifold M and you have a point P, then your tangent space look like this. So that would be the tangent bundle. I mean, it's a bundle of tangent spaces anyway, right? Yeah. So let's go towards vector fields now. So I take the example of S2 to help you visualize how it looks, and then we define it more general setting. So a vector field on the sphere S2 would be basically a map that assigned a vector, tangent vector to each point, something like this. Right? So you can think of such a thing as, let's say if this is a vector field X, then you can think of it as a map from the sphere to the tangent bundle of the sphere. So take a point in S2 and it gives you a vector X of P, and that vector lies in the tangent space at the point P. So each point you get a tangent vector in that tangent space. And that this map has to be smooth, so you get a smooth vector field. In general, if I look to, let's say, this is my sphere and these are the tangent spaces, then this function is basically take a point and it gives you a vector, then another point give you another vector, maybe a better vector. So you can draw it like this. So it looks like a section of this vector bundle. Section of TM. But that's more complicated language and you don't need that at the moment. I leave it like this for a while so that you can think about it. By general manifold, you can define it a similar way. In general, let's say you have a smooth manifold. Of dimension m, and let's say then a vector field on M is a map. Let's say X from M to the tangent bundle of M. So it takes a point and assign it a vector in the tangent space 8P. Make sense? Now you don't see how it looks like, but because the manifold you cannot visualize, you can't visualize the vector field. And I denote something called sections of TM. So this would be set of vector fields on M. And that's basically maps from N to okay. That's the notation. Remember it. It's called sections of the tangent bundle, and that's basically a vector space. You can multiply a vector by a real number, so you get again another vector because these tangent spaces are vector spaces. So this space of tangent vector fields, the space of vector fields is basically a vector space. It's a ring where the field of it's a ring where C infinity functions, but just forget that and think of it as a vector space. So in other words, if you have a smooth function, let's say, and you have a vector field, then you can multiply the vector field by this. So each tangent vector get multiplied. So that would be a vector field. So at each point, it would map to f of p times this vector. It would be again a vector. So p of f has a real world number and x of p is a vector. So if you multiply them, you get again a vector in the same vector field. So you can multiply vector fields with smooth functions to get another vector field. Okay. So for now, this is enough. Let's go towards Riemannian matrix. So what is a Riemannian metric? So let's say metric. So let's start with some nice examples. So consider, a path, comma, from this interval to R3. Right, something like this. You know how to define its length. The length of gamma, which I call L of gamma, it's basically the integral a to b of the absolute value of the derivative, of gamma. That's basically what you have learned in your calculus course, calculus 3, maybe vector analysis course. If you look a bit close to this formula, you can write it as like this. So you have the inner product, the dot product in the Euclidean space, gamma prime of t. So the prime denotes the time derivative. So you get two vectors, you take the dot product, and then you take this square root and you integrate. This is basically the norm of that vector. And this is basically the standard product, inner product, you can say. Interesting. Similarly, if you have two vectors, in R3, let's say P and W, you can define an angle theta between the two, and it is given by the cos inverse of something. It's given by the dot product of the two, and then you define by the norms. So the norms are basically given by, right? So you can, if you have inner product, you can define this length. So the conclusion is inner product gives a way of measuring, gives a way, sorry, lengths of paths and angle between vectors. That's something you already know. Now the question is the following. If I have a path going to some manifold M, so it's a smooth manifold. Now, you know, what does it mean to say that a function from the interval to M is smooth? Because you have a differentiable structure on M, and you can define the smoothness of gamma easily. So let's say gamma is a smooth function. So the derivative exists. Now, how can you define the length of gamma? If you go back to the Euclidean case, well, you can say, let's say I want to define it like this. Absolute the norm dt. Maybe I should say something else here. They said inner product. Square root. Now, this guy, if you look here, gamma of t is basically a tangent vector in the tangent space of M at gamma of t, right? So this inner product should be an inner product on the tangent space of that point. Another way, if you have a manifold and on each tangent space you have an inner product, then you can define lengths of paths like this. Okay. So this motivates the following definition of Riemannian matrix. This is not a precise way of defining Riemannian metric, but it gives you more or less the idea. So a Riemannian metric on M, so M is smooth manifold, is a function that map each point in M to an inner product. It is denoted by this at P on the tangent space at P. So each point is a function that assigns each point an inner product on the tangent space at that point. And second condition, I want the map, this map, so should be smooth. I don't want to define what does it mean to say that this inner product varies smoothly with the point P, but let's assume it's smooth in some sense. That's a Riemannian metric. Simple example would be Well, so let's say the Euclidean space is your manifold M. Well, the standard product. So you have basis vectors. If you can define it for that, you can define it for any vector then. So let's say the Kronecker delta. It's 1 equal 0 otherwise. That's the standard inner product. But of course, you can define it, many ways. You can define other standard other inner products on Euclidean space. So a bit, let's say, non-trivial example. Let's say my manifold is now the sphere. And if I take two vectors in the tangent space at some point to the sphere, then this tangent space sits in R3. So these two vectors, you can see them vectors in R3. And I define the inner product on the sphere for these two vectors to be the standard vector, the standard inner product above. So in the example 1, let's say. So now you have an inner product. This inner product is called the induced inner product or the standard inner product, a standard Riemannian metric on the sphere, by the way. So now you can define lengths. So I give you the following question. You have this sphere. And let's say take 2 points, P and Q. Now you can take a path from P to Q. Now the question is, which path is of shortest distance? Right. So which path? So a path would be a function comma from, let's say, 0 to 1 to the sphere, which starts from the point P, ends on 1, a point Q. Minimize length. What is the path of shortest length between the two? Well, you can turn it to a problem of calculus variation that I'm interested in to talk about in future. So how can you turn this problem to calculus variation problem? So let's define something. C infinity 0 to 1 is 2. Define this to be maps from 0 to 1 to the spheres. It should be smooth. Secondly, it starts from the point P and ends in Q, right? This is not a vector space because you get two vectors on S2, 2 points on S2, and adding them would not give you a point on S2. So it's not a vector space at all, or Banach space or something. But you can define a functional, it's called length to R. So take gamma and map it to the length of gamma. And the length, is now from 0 to 1, gamma prime. And this is basically the induced inner product on S2. Now, the paths of minimum length are basically the critical points of this, or the minimizer of this functional. So the question is, does L has misers in this space above? And in future, I might give you proof using direct methods and calculus variation to prove that at least something exists. Okay, but you can think about this problem in your home. Okay, so I'm going to now define affine connection and tell you what they are, but before that I gave you like 10 minutes break and then we would be done. So it's just the definition of affine connection and some motivations. So we have now background for to understand affine connections. So see you in a while.
This meeting is being recorded.
Okay, so what is an affine connection? So that is what I wanted to talk today. So okay, so let me motivate this before I define it. So let's say, consider a vector field. On R3. So that would be basically a function x from R3 to R3, right? So if I write, so each point gets a vector. Each point P, you get a vector xp. So something like this. You know what does it mean to say a vector field is constant nRn? So x is constant or parallel. You can say parallel as well. If it equals some c for all points and some vector. It's a fixed vector, and this vector field is equal. And in this case, it looks like this. It looks parallel. That's why it's called parallel. So it would be, let's say, same vector everywhere. Same vector everywhere, right? That's what it means to be constant, right? Now, good. So you know how to define, a vector field being constant. So in Rn. Now the question will be the following. Let M be any smooth manifold. Right? And Y be a vector field. So it would be a vector, it's a function from M to the tangent bundle. It's a vector field. Now, what does it mean to say constant? To say Y is constant. Okay. The problem is, this definition that Y of P equals some vector for all P doesn't make any sense now because of the following reason. Let's say you have a point, this is your manifold, this is point P, and you take another point Q. You have a tangent space here at P, and you have a tangent space here. Now, if you say this thing is true for all P, now this C is a vector field in the tangent space, is a fixed vector in the tangent space at P here. And then it is also for this vector space. So these tangent spaces are different because they are in different positions. And you say C belongs to both vectors, both tangent spaces. And these are different vector spaces. So this definition really doesn't make sense at all because the tangent space changes as you change the P. So how would you make sense of a constant vector field on manifold, right? No? Or maybe parallel, if you can say. So let's go back to our observations in the Euclidean case. When do you say a function is constant, by the way? I mean, you have a smooth function and you say it's constant. What is another way of saying this? At least there is at least one way that you can say the same thing. Can somebody say it? When a function is constant, when a smooth function is constant, I mean, use some calculus to tell me.
If its derivative is zero, is zero.
Exactly. If its derivative is zero. So back to the Euclidean case, if you take vector fields, you have a nice derivatives. So if you take, if you have, let's say, the set of vector fields in R3, and then you have, let's do it the other way. So if you have two vectors, let's say X and Y, these are two vector fields on R3. And you know how to differentiate one with respect to the other. So let's say I differentiate to Y with respect to X. That is simply, you add X to let's say some perturbation of X minus Y, something like this, limit. That's how you define a vector field, the derivative of one vector field with respect to the another one. And so this derivative has the following definition. You can think of it as like, D. So it's a function from the vector fields times the vector fields gives another vector field. So it takes a vector field X and another vector field and differentiate Y with respect to X. And that derivative is again a vector field. So it's a function from this product to that. But it's not just a function. It satisfies some nice conditions. Well, the first condition is it's linear with respect to the first argument, which would be like, if you have, let's say, two other vector fields, X and Z, you add them and you differentiate Y with respect to the addition, you get the derivative of Y with respect to X, and then the derivative of Y with respect to Z. That's the linearity. And then you have, let's say, if you multiply a function, a vector field with a function, and then you differentiate Y, you simply bring F to the front and then it's Y, and where F is basically a real valued function, right? That's the derivative, linear by definition. Then you have another property. So if you take two vector fields, sum them and differentiate with respect to X, you get linearity even here. So like this. And if you multiply a vector field with a function F, and you differentiate with respect to X, then there is this Leibniz rule. So you bring the function to the front, differentiate Y with respect to X, plus you differentiate the function, that's the directional derivative of F, and then you multiply it by the vector field. And then this F is basically from R3. It's a smooth function. This is true for all vector fields in R3. So the above conditions hold for all vector field and all functions. Okay. So you have this nice derivative, which you define something like this, you see, and by the definition, and this satisfies these nice conditions. Now, well, if you can define such a derivative in a manifolds, then you can make sense of parallel or constant vector field, right? So a vector field now in this definition would be constant. So with the above definition, let's say a vector field y is constant if the derivative above I defined is 0 for all vector fields. So you, no matter in which direction you differentiate it, you get 0, and that would mean that y is constant, right? Or parallel. So now, if you have such a derivative on manifolds, you can still define the same notion. So let's go to the definition. That derivative, such kind of derivative on manifold is called a connection. So let M be a smooth manifold. Right? Now, an affine connection on M is a map. So it's a map, let's say Nabla. Is it Nabla, I think? Okay. That you have, say, vector fields on M. Remember, this was the space of vector fields times space of vector fields into the vector fields. So it takes two vector fields, x and y, and differentiate y with respect to x, and you get another vector field as above. But it has to satisfy the conditions of derivatives as above. So is linear in, okay, so let me properly state that. So if you have a function, multiply, then you bring the function to the front. Similarly, x plus z differentiate y. I'm just restarting the above, so just quickly try it. And third, so y plus z. So these x and y and z are arbitrary vector fields. They are not fixed. And the Leibniz rule. So it should give you yes, and then the derivative of f with respect to x and y. This should be true for all vector fields, sections of the tangent bundle, and smooth functions. Functions from M to R, the real valued functions. This kind of mapping, is called an affine connection. And there's a theorem that every smooth manifold has at least one affine connection. I mean, there are many, but there exists at least one derivative like this. And we don't call it derivative for another reasons, but it's basically a derivative of one vector field with respect to another. So the conclusion would be, so just an affine connection gives a way of differentiating one vector field with respect to another on manifold. Okay, nice. So now let me give you some examples. So let's say simple example. Take M to be the Euclidean space. By the way, if you go back here, this map is linear. So if you can define it on some basis, then you can define it for any vector field because it is linear. So we know that these vectors AIs for I1 to n, this form a basis for Rn. So if you define, let's say, the derivative of Ei with respect to Ej, then say for all I and j belongs to 1 to n, then you're done. So let's define it by Kronecker delta. So if I and j are equal, this is equal to 1, or they're not equal to 0. This gives you a derivative of vector field. And this is what you see the Newtonian derivative in calculus. It's the standard derivative. Now you can, here I define it like this, but you can define this to be anything, any vector, or maybe some vector field, and then you get a new derivative. So let's say I define it the following way. So in the same Rn case, for the same example, I define my affine connection to be, let's say Ij. Let's say they are equal to 1 for all I and j. Well, you got another derivative. So you can do calculus in a new way. So basically, I think these are basically n square choices. So once you fix these n square choices, you get a derivative. And you can do calculus again. So on the Euclidean space, you have infinitely many wave derivatives. Definitions of derivatives like that. Now the question is, which derivative is a good one among all these derivatives, right? So is the following theorem. Let you have a manifold with the Riemannian metric G. So let's not call it G because I didn't denote it by that way. So this inner product notation. So let's say you have a Riemannian manifold. And now then there exists a unique affine connection. Connection is called Levi-Civita connection. That satisfy the following condition. So if you take 3 vector fields from n, then you plug it in the Riemannian metric, you get a smooth function. So for each point you get an inner product, so it's a real number. So now this is a smooth function from the manifold to R. So you can differentiate it with respect to the third vector. So differentiating this smooth function with respect to x should be the same as the derivative of y with respect to x inner product plus y the derivative of z. So it's in the standard dot product in Euclid has this property at all. And then there is some symmetry condition. So y is symmetric. This means that if you differentiate this standard vector I with respect to j, it is equal to differentiating j with respect to I. So you can switch the partial derivatives. Something like so it's like square xi xj. You can write it like xj xi, something like this. Yeah, you can switch it. So this connection is unique, and it's called the Levi-Civita connection. So going back to the Rn example, you have infinitely many differentiations, and which one is the best is the one that satisfies this condition and this condition, and we know what they are. It's exactly the derivative you see in the calculus. So the standard derivative is basically the Levi-Civita connection in Rn, but you can define infinitely many. Okay. So I think so if you have now in a fine connection, you can define something called covariant derivatives. So it's basically the derivative of vector field along a curve, and it comes from an affine connection. And if you have covariant derivative, you can then write down differential equations on manifolds and so on. So I would just roughly write it down. Let's say if you have, let's say, a curve to your manifold and you have an affine connection delta. So now the derivative of this function with respect to t is basically a vector tangent to m at the point gamma of t. So let's say right. My manifold, this is gamma. So that would be a vector, something like this. Now you have this vector field. So gamma prime is a vector field along gamma. So now you can differentiate this vector field with respect to itself, right? Because both vector fields. So you can write down, let's say, the derivative of something like this of the vector field. And let's say equal to 0. This is basically a second order differential equation whose solutions are functions from interval to the manifold. It's a second order different system of differential equations. And so, and the solutions to this equation is what we call geodesics. And basically these are paths which minimize the length between the 2 points and so on. But I think there's a different story, and it really requires some strong background to continue. And in one lecture, I cannot, explain you everything, but I more or less gave you the idea of a lot of things. And if you're interested to read more, you can go and take a differential geometry book and keep in mind what I said here. probably you would be able to understand what they're writing. So this lecture should enable you to read some text on differential geometry yourself. That was basically the main goal of this lecture. I think I should stop here. Okay. Wajid? Wajid?
I think he is busy somewhere.
Hmm?
I think he is busy somewhere. I don't know.
Yeah, that would be a trivial implication.